Hi, and welcome to the improved digital model on geothermal environments. In the second part of the module, called Soil Complexities in Geothermal Areas, we will explore the characteristic of soils, and we will learn about the methods to investigate their properties, and also we will cover how soil alteration can change their properties, in particular permeability and strength. And changes in these properties in turn can affect surface fluid circulation or lead the formation of hard grounds or structures or the creation of unstable ground conditions. Throughout this module, you will gain a comprehensive understanding of how we map soil distribution and how we estimate the impact of soil properties on surface degassing in geothermal areas, or how certain type of geothermal settings are formed and which are the role of soil in it. Before we discuss the method for soil characterization, let's quickly define soil horizon. A soil horizon is a distinct layer of soil beneath the surface with unique physical, chemical, and biological properties. This layer can be identified by features like color or texture. Typically, soil have an organic surface layer called the O horizon and a mineral layer starting with the A horizon. Subsoil layers that are more developed are called B horizon, while less developed ones are C horizon, and the original bedrock layer is usually referred as R horizon. However, different types of soil can have different horizons, which can be identified based on other factors. In non-volcanic and non-geothermal areas, forms mainly through the weathering of biological activity. However, in active geothermal areas, soil formation is also affected by the type of volcanic material which is present and how these materials are changed by circulating fluids which are arising from the shallow hydrothermal aquifer. Recent studies have integrated organic characteristics with geological strata and thermal fluid changes to characterize soils. In this example, we have the unaltered and undisturbed Taupo pumice, which works as a benchmark in the Rotokawa steam field region. You might remember the Taupo pumice deposits as being the most widespread deposit around the area from the first part of the module when we discuss about it. The deposit consists predominantly of fine, coarse-grained portion, which might contain or not numerous and large pumiceous fragments. Vegetation growth and the circulation of thermal fluid can significantly influence these soils, leading to diverse textures and properties. This process has, at least in the steam field area, has resulted in the development of at least four types of soil in addition to the unaltered version. In our fieldwork, we employ several tools to analyze soil characteristics, and these include mostly two permeameters, the PL300 designed for general soils, and the tiny perm tree, which is used instead for very stiff and soil rocks. We also have soil moisture sensor for measuring humidity levels, thermocouples to measure temperatures, and as well we have pocket penetrometer and vane tester for assessing compression and shear strength. Overall, our instruments cover a wide range of permeability values which are essential for both permeable and impermeable soils. As for the mechanical properties, our strength measurements they span from very soft to hard soils. The procedure shown here outlines the practical step for using the PL soil permeameter device. Initially, the soil layers are exposed using a shovel and spades to distinguish the different horizon or layers. Then an horizontal step is prepared at the top of the layer, which is chosen for sampling. A ring cylinder is then positioned vertically on the step and is driven into the ground using a stump and a hammer, which is down here. Once the cylinder is filled with soil material, is extracted delicately using spatulas and is prepared for measurement. Soon after the removal of the cylinder, what we usually do is we measure ground temperature at the in the specific spot where we took the sample, and we also use the area which are undisturbed around the layer to take measurements of compressive with compressive and shear test devices. Typically, for each measurement of compressive and shear test, we take between 6 and 12 measurements, which are usually used to get average error values and associated error to the assessed properties. And at the same time and after uh, the the collection of the sample, we also use our Moster device to measure the humidity in the very proximity of the collected sample. Then the cylinder is initially wrapped in a cling film to maintain its original humidity level, and is weighted with a scale. Subsequently, the film is removed and the cylinder is mounted to the soil perm, where we basically can start measuring our PL value, which is like a sort of a pneumatic conductivity or hydraulic conductivity, which can be later converted into air permeability. Typically, this procedure is conducted outdoors under optimal weather conditions, and but in case of adverse condition, as you can imagine, for example, working in Iceland, it might be that in many of the days being there, you might have rain condition, or you can have strong wind condition and snow and so on and so on. Basically, we took the cylinder indoors, and we measured the properties of the sample within few hours from the wide-row. Comparing measurements taken from outdoor and indoor, it confirms the reproducibility of the results, and also allowed us to validate reliability of the used method. So returning to the Rotokawa geothermal steam field, here there is the map which was presented and discussed in the first part of the module. As we proceed with identifying various thermal features within the three primary domains, we simultaneously begin to classify and sampling soils. Additionally, we selected and described specific soil profile that represented distinctive thermal features. Our aim was to capture the properties of the primary Taupo pumice in its undisturbed section, near collapsing structures or unstable ground areas, within excavated zone, near the gassing spot, and measuring the properties of sinters around pools, or among the others. So in the end, we classified 11 soil horizons. 5 were like including the top of pumice unaltered and 4 altered version of it. 3 included material from excavated areas. 2 are like sort of contact soil between the reworked and the main type of soils. And then we also characterize the present soil, which is affected by, it's like the unaltered taupo affected by vegetation. The soils were categorized by origin and features. The undisturbed pumice deposit could have like a fine-grained dominant component and be moderately to highly altered, or have like a dominant coarse pumiceous component and again being moderately or highly altered. You can see that in both cases alteration can increase to a level such as can destroy or obliterate completely the main characteristic of the deposits. And in some cases, the sulfur can even completely replace the pumiceous component. Then we have reworked materials characterized by the E1, E2, E3, which is mostly made of material excavated, and it's mostly loose with sandy or silt components, and can have different proportion of pumices. We saw also that in some cases this deposit can be completely altered and cemented by sulfur minerals. Then we also have like other layers that include the contact material, which again is more dominated by a clay component. In average is quite highly to moderately to highly altered, and many times most of the features of the original deposit are completely lost. Another soil type is the mud, which is dominant in many of the mud pools around the feature we recognize and discuss in the first part of the module. And finally, we have also the soil S, which is like oxidized soil and full with most of the time filled up with roots and organic material. And each one of the soil, of course, has like its own distinctive, not only textures and aspect, but also distinctive permeability, porosity, compressive and shear strength. During our study, two distinct type of soil profile were investigated. One was the one we excavated in the ground to understand subsoil properties, and other type of soil we looked at were the one exposed in the proximity or near fumarole or steaming areas or unstable grounds. Our measurements they focus on the petrophysical properties and laboratory analysis of the soil samples, and the in situ measurements were complemented by some laboratory tests, for example, to determine their density and porosity. Here in this plot, we can see basically our permeability, compressive strength, and shear strength. They vary as a function of porosity and intrinsically due to their alteration state. Now to show this, I'm just going to select some of the material, for example, from the Taupo deposits in its fine to mid grain size type of soil. So throughout the undisturbed and excavated site, the silt and sand-rich Taupo pumice layer, they exhibit a variety of porosity, permeability, compaction, and alteration. In particular, the ash or the fine component dominated layers, the T1 to T3, range from sort of like low porosity in the proximity of, well, far away from sort of like altered area to increase in porosity approximating like a vent or fumarolic spots or degassing sites. So as depicted in this plot, a high degree of alteration, so going from T1 to T3, can significantly increase porosity and permeability, while it's decreasing the compressive strength and the shear strength. However, in some cases, for example, the shear strength in some of the areas may increase in sort of intermediate conditions. The reduction in both strength components becomes more and more predominant in areas where unstable ground, for example, and collapsed structures are present. So, comparing soil profiles across different areas shows varying distribution and relationships with the observed thermal features. Just to bear in mind that in few cases, or when we were like, for example, having soils which were too hot or too fragile or too humid, we could not measure permeability of the soil, so we could sort of infer their degree of permeability by looking at their textures, or for example looking at the temperature profile or value within this level. So Taupo soil in general, like the layers with undisturbed or like slightly disturbed and altered, the one which have fine-grained material as dominant proportion, they generally show low permeabilities, which can go to 10 to the minus 15 to 10 to the minus 16. They can have generally high or mid values of strength, and they have temperature which can be kind of below 50 or very low, even below 30 degrees C. The properties of this type of soil can change when pumices are present within it. Pumices in general, both in an altered or altered condition, they can have like higher porosity and mostly higher permeability. So if present, if their presence is abundant within the layer, they can change and favor the circulation of fluid within that level. If we look at this profile E1 and E2, for example, T3, again, we don't have permeability value, but the textures and the temperature profile, we could infer that the T3 layer and T4 might have a decently high permeability, allowing to the fluids to rise, the hot fluids to rise closer to the surface. And in the case of the E2, we can see that large Prometheus level at depth, we have permeability around 10 to the minus 13, and also a bit more altered and more compacted. Probably they have a slightly lower permeability at 10 to the minus 4. And in this case, we are very close to a fumarolic vent. So the combination of the proximity to a hot feature and the decently high permeability allow for a very high temperature to be reached within like about a meter and a half from the surface. In other cases, the presence of like porous rich layer, like in this soil profile in year 10, they can change again the permeability and allow for better fluid circulation in the horizontal direction. For in this case, we have like a cemented brecciated level at the base with a permeability around 10 to the minus 16. And then we have like excavated material with a fine dominated component at the top and excavated material in between, which has a bit higher permeability. And this can be mirrored by the fact that the soil, the temperature profile has a sort of a positive bulge, thanks to the, again, to the hot fluid, which could move in horizontal direction. In these other two cases here in section or profile S1 and soil section E9, we can see instead the effect of the presence of level which have a lower permeability close to the surface. In this case, we have a series of excavated material, which the dominant part on the top is ash rich, or we have in this case in the middle part we have a part of the soil which is dominated or by the presence of completely sealed and cemented level by native sulfur. So the effect of this is like to create a sort of a thermal buffer for which the fluids can sort of like hot fluid can reach the part where they're present, and there is a rather steep gradient of temperature due to the fact of this low permeable level, which again they act as like sort of a cap to buffer the temperatures. Together with the properties we just discussed for the soil that we measured, we also implemented the measurements of near surface soil temperature around 10 to 15 centimeter, as well as that of the water. And you can see in this map here on the right, there are like the different section indicated as E or S, and there are all the black dots which represent the area where we took measurements of these temperature values. While with the soils cemented in our ground, we used digital thermocouple. For water temperatures from spring and pools, we use wired thermocouple, which were positioned as close as possible to the bubbling vent area or within the vent area itself if the pool was small enough. As you can see here, we have the map of the thermal distribution. We go from very cold temperature around 5 degrees C up to temperature which approximate 100 degrees C, which is close to the boiling point of water around Totokawa area. At first glance, you can already recognize that as well these thermal anomalies, they sort of distributed along preferential direction, mostly northeast, southwest, or there are also the strongest anomaly of the fissure that alienates quite well in the east-west direction. So now here we have again the map of the thermal fissures around the steam field area, and basically our result again suggests that the distribution of natural and mining related geothermal features aligns with area of varying degassing intensity, and this area aligns usually along linear or circular pattern. For example, as again in domain 1 to domain 2, most of the collapsed structures and spring well fit with this pattern, or as you saw also from the temperature anomaly, the fissure goes more east-west, and there are other features which more follow more like this curving lineament here in the domain 3 or close to the lake, or in this area northeast of the steam field, which we didn't really discuss but contain mostly collapsed structures. So this suggested the connection with the subsurface faults or eruption crater rims, in particular the prevalence of collapsed structures and spring in the north, east, southwest. It's mirroring like the effect of the deeper fault system in the Rotokawa, and in particular what is called the central fault field, which allows for fluids to rise exactly in this area. While all the curved elements, they correspond basically to all the border of the explosive crater, which produce hydrothermal breccia that we find within the steam field area and outside. Concerning the role of the soils in the distribution and the characteristic of the thermal feature, basically the results show that fine-grained or clay-rich soils can basically have a low permeability and be in average decently stiff, and basically they're sort of influencing the hydrothermal degassing towards the surface or in the horizontal direction. In contrast, all the permeable pumice-rich layers facilitate the rapid fluid migration. In this example here, we can see that the presence of porous layers, porous materials sort of like allow for fluids to quickly rise close to the surface. This can justify that the presence of thermal anomaly around this kind of site, or as we remember from the case discussed before, the presence of this layer between other material of lower permeability can allow the fluids to move horizontally and produce a sort of like thermal anomaly in the vertical profile, or thermal bulges. The other effect of alteration is also basically, again we can see from these two soil profiles that the alteration can strongly decrease the compressive and the shear strength of the rocks, and again favor the formation of unstable and sinking grounds, which again are the most, or actually the most dominant feature all around the steam field area and outside. You can see again that they are quite widespread all around thermal activity, thermal degassing feature, or around collapsed structure in domain 1, domain 2, and domain 3, and here in particular around the main and large fissure. Then in the end, after having characterized and measured the properties of the main soil type, and having characterized all the soil profiles, the next step basically to follow is like to put together all the information we collected in the study of our area, of our geothermal environment. So of course we do start with the thermal features which were mapped, so we used that as a tool to understand again the distribution, the nature and the distribution of the main thermal features. Then on top of this first layer of distribution of the features, we could start putting the bricks of the soil profiles and their main characteristics in terms of permeability, strength, and temperatures. So all these components together, they basically allow us to move to understand the next level, which is like sort of the the implication of large scale of geological, structural, and hydrothermal setting, and which is the relationship between the deeper portion of the system with what is happening at soil and subsoil level. By combining all these elements, in the end, we can arrive to the point where we can build conceptual model of the main thermal features in the Rotogawa steam field, or anyhow, this method can be applied to any geothermal environment under study. And this conceptual model, which sort of like embed all the um, quantification of the properties, their change with the effect of alteration, and their possible correlation with deeper structures. So this one and the next cross-section across domain 1, 2, and 3 will illustrate how thermal features interact with the soil pattern in the steam field areas. And in this interaction reflect, I repeat myself again, but this interaction reflect the influence of the thermal system and mining activities on soil properties such as permeability, temperature, and strength. Differences are observed between areas which are near to the water table, so near to the Lake Rotokawa, and those which are 10 to 20 meters above, so mostly are in domain 1 and 3 in the eastern and northern part. Near the water table, mud deposits, sinters, and stromatolite can form, and together with warm spring and hot and mud pool fed by um, the upflow fluids from the hydrothermal system. In the vadose zone, so in the large relieved area, the leaching and degradation from below and the degradation of the taupo-pumice can create weak and stable soil and collapsed structures, especially in areas which are in correspondence of the main fractures. And as well, they allow for the rapid rising of fluids which are rich in sulfur and allow the formation of sulfur encrusted ground or sulfur rich soil in the excavated and surrounding areas. And here we just have, like what we call in the base, exactly these two sort of a member. So the lagoon with a large amount of springs and the presence of mud sinter or stromatolite and so on, while in the relief area the formation of collapsed structure can go from a structure having like few meter size up to gigantic feature having order of 40-45 meters. Within mining areas, we observe tuffo deposits in various state of alteration, ranging from unaltered to highly altered. It is likely that the fracture system beneath the surface which allow the altering of these deposits, it was the same before and after the removal of the clay cap during the mining activity. The undisturbed and altered taupo characteristic are probably related to the condition existing in before the mining commenced in the area more far away. Post-mining alteration have significantly transformed the deposit by sort of like calling up for fluids which distributed all within the excavated area and laterally where the presence of permeable level, or basically the soils or horizons of soils rich in pumice were present. And this post-mining alteration basically allowed for the again the alteration at different stage of the taupo in its different phases from fine and coarse grain, and as well as allowed for the alteration of the excavated material, which was also thrown on the side, and to the formation of encrusted ground together with like cemented grounds, which are frequently observed exactly within the excavated area and outside of it in the pile materials in all the main domains. So this again is one example from one domain one. You can clearly see exactly what is in this sort of conceptual model. The patchy crusted ground all around, the altered clay material, and well, it's out of the picture of course, but like you have to imagine that some of this cut you will see the taupo going from its unaltered state to zoning of differently intense alteration. Coming to the domain 3, where you have one of the most interesting and hot feature. This feature is basically running east-west, as repeated many times in the previous slide, and is characterized by its alternate and crumbly and unstable ground with collapsing edges. This feature basically developed along what is geological discontinuity, such that there is like a crater border of one of the hydrothermal eruption events in the area. So basically what we have in this situation is that we have the deformation of the explosive crater which formed the breccia, and the post-emplacement of the Taupo-Pamis. The presence of this fractured zone related to the explosion allowed for the rising of a large amount of fluids, and this basically intensely leaches and alters the Taupo-Pamis and portion of the erupted breccia and part of the old substrata, which is made by an Ingram-Bright deposit called Oronui Tuff deposit. To conclude and give some key points from the study presented here in this second part of the digital training module, I just want to highlight the critical role of soil properties in shaping the dynamic of geothermal environments. Soil characteristics such as granulometry and alteration state can significantly influence the fluid circulation and the manifestation of thermal features like mud deposits, sinter, and so on and so on. Nonetheless, the degassing dynamic and the sites where the degassing can occur and at which intensity. We employed a comprehensive approach combining field measurements observation with laboratory analysis to map these thermal features, define soil types, and assess the alteration degree and patterns. This integrated method basically provided the detailed insight into surface expression and their related potential hazard. And this assessment was supported by a robust data set of soil properties, which are indeed essential for accurate hazard assessment in similar geothermal settings to Rotokawa in New Zealand and many other places in the world. So here we reach the end of the second part of the digital training module, the soil complexity in geothermal areas. As in the previous part, here we have the cited literature, plus some further reading, which I strongly recommend if you want to learn more about the described and discussed methodology applied to different geothermal settings. I thank you one more for been sticking around, and I look forward to see you in the third part of this module.